Good evening, everybody. My name is Francisco, a fellow student in Intro to Machine Learning for the Physical Sciences. Given the current conditions of the world and with the spirit of Christmas in mind, let us make some magic by making the invisible visible. So unfortunately, we didn't have a magical wand or an invisibility cloak, but in fact, we had something much better, which is remote sensing. In our project, we decided to analyze the latent heat flux, which is the movement of water from the Earth's land surface into the Earth's atmosphere. Unlike precipitation, ET, or the latent heat flux, remains hidden to our eyes. Our eyesight is limited to the narrow region of 400 to 700 nanometers of the electromagnetic spectrum. Therefore, remote sensing satellites are equipped with special instruments such as a spectrometer or a radiometer that enhance our vision into the spectrum. In a sense, these satellites make the invisible visible. This is where the magic occurs. The information that we're able to derive from these measurements it's incredible. We're able to derive things such as temperature, spectral emissivity, and albedo, but for our purposes, we're interested in plant photosynthetic activity. In our regression, we'll be using the Enhanced Vegetation Index, or EVI, as one of the variables. If we look at our plant here with a spectrometer, we'll get the following values of reflectance.
EVI uses the difference in the near-infrared and visible portions of the electromagnetic spectrum to determine the strength of the red slope between chlorophyll and mesophyll. The higher this slope is, the more indicative that photosynthesis is occurring within the leaf structure.
For one of the dependent variables, or the Y target values, is the crop coefficient, or Kc. The Kc is simply a ratio of actual to potential evapotranspiration. Actual evapotranspiration is usually calculated through eddy covariance systems, and reference evapotranspiration or potential evapotranspiration could be calculated anywhere with basic weather data. In the spirit of random forest regression, we decided to use data from a woody savanna ecosystem situated by Sacramento, California. We used random forest regression in order to isolate the most important features within our dataset. As expected, we saw Kc and EVI being ranked highest, and surprisingly, our first finding was that the vapor pressure deficit, or VPD, which is measured in kilopascals, was ranked third highest. We then used a ridge regularization between our top three features, which yielded in this equation. And finally, we then used ordinary least squares between our top two ranked features, which were Kc and EVI, and it yielded this equation. We can now calculate Kc as a function of EVI using this equation. We derived this equation using an ordinary least squares method, and the equation itself has a plus minus 10% error. Therefore, estimates should be used with caution. As we stated earlier, ET0 can be calculated with any basic weather data. The equation now, we can now calculate ET using this equation. Again, we get ET0 from any basic weather data, and now we have a function that predicts Kc. Kc itself could be derived from most remote sensing platforms which have worldwide observations. The equations that we derived in our project have the potential to be implemented across woody savannas of the world, where problems such as shrub encroachment, drought, and climate change present new challenges and risks in terms of water management. Our equation still needs further work though. It's not done. There's lots of work to be done, more variables to test, so therefore stay tuned for the PhD. So there it is, everyone. There's the magic. We made the invisible visible using the machine learning algorithms that we learned throughout the quarter. Please leave any suggestions or comments down below. Don't forget to click like and subscribe. And as always, thanks so much for watching. We'll see you next time.